So these notes are going to focus on dividing polynomials, so long division, synthetic division, the rational zeros test. So finding zeros using the P over Q method, finding all the possible rational roots, and that type of thing. So we're going to go ahead and jump right into it. Our first example here is going to focus on using long division in order to find the quotient and the remainder here. So right above here, this is essentially just saying we have our f of x, that's called our dividend. We're going to divide it by our divisor here, the d of x, and our answer is going to get, just like we do any kind of division, like if we do 7 divided by 3, right? We know 3 goes into 7 2 times. It would have a remainder of a 1, and we would put that over the divisor of a 3 there. So same instance here. When we do this division, we're going to think of it as like our quotient, our whole number part here, that q of x. And then plus our remainder is how we are going to write that. So let's just go ahead and jump into it. This is what it's going to look like. So I'm going to rewrite the problem. What we're doing is 4x cubed minus 2x squared plus x minus 3. And we are going to divide that by the 2x minus 3. Now, when we do long division like this, what we do is we focus on the leading terms of our dividend and our divisor. So that would be the 4x cubed and the 2x. And we want to divide 2x into 4x cubed. Now, if we're trying to divide 2x into 4x cubed, it has the same meaning. Keep in mind, multiplication and division go hand in hand. So if I'm trying to divide these together, it's going to also look like 2x times what would give me 4x cubed, right? 2x times what is 4x cubed? Well, 2 times what would give me a 4? Well, 2 times 2 is 4. And then x times what would make it x cubed? Well, x times x squared, right, gives you x cubed. So I'm going to say that 2x times 2x squared is what's going to give me this 4x cubed. So I'm going to put the 2x squared up here. Our next step in division is to take this here, and we're going to multiply it times our divisor. We're going to take that 2x squared, multiply it by 2x minus 3. Distribute that out. 2x squared times 2x is a 4x cubed, minus 2x squared times that 3 is a 6x squared. We are going to bring that down here. So let me see, 4x cubed minus 6x squared, and we are going to subtract that away. 4x cubed minus 4x cubed goes away, that is 0. Negative 2x squared minus negative 6x squared. Be careful with your signs here. Remember, we're doing a negative 2 minus a negative 6, right? Negative 2 minus negative 6. Double negative rule there makes that a positive 4x squared. Drop down your plus x minus 3. Now we're ready to divide again. Now we're going to look at our leading coefficients again. So we're still looking at a 2x over here. Now we have a 4x squared. All right, so same thing here. We're going to look at our 2x. 2x times what is going to give us a 4x squared? Well, 2 times 2 is 4. X times another x would give me an x squared. So I'm going to say that 2x goes into 4x squared 2x amount of times. And it's positive, right? This is positive. This is positive. We can stay positive here. There's no need to put a minus sign there. So let's multiply. We're going to take that 2x here, multiply it times your full divisor, the 2x minus 3. Distribute that out. 2x times 2x is 4x squared, minus 2x times 3 is a 6x. Write that in here. So we have 4x squared minus 6x, and let's subtract that away. When we subtract, 4x squared minus 4x squared disappears. You're going to be careful with your signs here. We have a positive 1x minus a negative 6x. All right, so again, so positive 1x minus a negative 6 is what we have going on here. Double negative rule there makes that 7x. And drop down that minus 3. Now for our last division here, going back to our leading terms, now we're looking at a 2x and a 7x. So same concept here, 2x times what is going to give us a 7x. Now, let's pause here for just a second here, because look, we're turning a 2 into a 7. Or we're seeing 2 times what is going to give us a 7. X times what will give us an x. Well, we have one x. We have one x here. No need to multiply by any more x's. So we really just need to figure out what is going to turn this 2 into a 7. Well, a 7 halves. Because think about that. If we multiply 2 times 7 halves, or you can put that 2 over 1, the 2 here is going to cancel with this 2 here, leaving us with a 7. So we're going to say that 2x times 7 halves is going to give us that 7x. So let's add that 7 halves there. All right, essentially, if you have any numbers like this that are going to go in easily with each other, just make this one here your denominator. The number you're trying to turn it into is your numerator, so that they can easily, nicely cancel out. Otherwise, I'm going to go ahead and put that 7 halves up here, which means our next step is to take that 7 halves, multiply it times our full divisor, the 2x minus 3. When we do that multiplication, well, 7 halves times 2x, again, the 2's cancel, leaving us with 7x. Drop down the minus sign. 7 times 3 is 21. 21 divided by 2 just makes that 21 halves. Subtract 7x minus 21 halves. 7x minus 7x cancels. A negative 3 minus a negative 21 over 2. Throw that into your calculator. You get a 15 halves. So the way that you write your full answer here, right? So I'm going to write it in this space right over there. So think of this part. This represents our q of x here, our full quotient, which is the 2x squared plus 2x plus 7 halves. Then we are going to add our remainder. So we are going to say plus our remainder is, well, 15 halves. And you put that over your divisor, which is the 2x minus 3. Now let's talk about the synthetic division process here. So when it comes to dividing or using synthetic division here, so we're going to take a polynomial equation. We are going to divide it here. Now, the important thing to remember about synthetic division is that your divisor needs to be in the form x minus a, or technically x plus or minus a. Right? There can't be a number in front of the x other than 1. Right? So like 2x minus 3 would not work. But something like x plus 7, x minus 3, that type of thing. X has to have a 1 as its coefficient, followed by a number. And typically, when we think about when we're solving a lot of types of polynomial equations, typically up until this point, we've solved them using factoring, maybe throwing into a quadratic formula, doing some other slightly different methods like that. Now, when we're solving using synthetic division here, so when we're dividing here by something like x plus 2, again, that is our divisor. You want to think of that as like x plus 2 was our factor that we're using, which means, if that's the instance and we're solving, one of the first things we tend to do there is set that equal to 0, and we solve for x. So we would subtract 2 on either side, and x is actually a negative 2. So that's important to understand, because when we do this division and it gives us x plus 2, that actually represents a negative 2 for our x. And it is the negative 2 that we're going to plug in and we're going to use for our synthetic division. All right, so x plus 2 really means a minus 2. X minus 1/3 would actually mean a positive 1/3, right? Because we would add that 1/3 to the other side. Otherwise, put that number in the corner in the box to the left. Take your polynomial and write its coefficients. So we have our coefficient of a 2 for our x cubed term, a negative 3 for our x squared, a negative 1 for x to the first, and a positive 2 for our constant. Draw your line, drop down the first number, and get ready to divide. So synthetic division, take the number, multiply it times your divisor. 2 times negative 2 is negative 4. Put that in the column to the right. Add that column, and we get a negative 7. Multiply again. Negative 7 times negative 2 is a 14. We put that in the column to the right and add. That gives us a 13. Multiply again. 13 times -2 is a -26. And when we add that column, we get a -24. So what this tells us here, we are done with the division process. When you're done with the division process, you mark off the rightmost column. The coefficients, or the numbers down here, are the coefficients of your new polynomial here. The number in the bottom right corner over here does represent your remainder. So that is going to look like a 2x squared minus 7x plus 13 plus our remainder. But since I have a minus 24 here, I'm actually going to put a minus 24 is our remainder over our divisor of x plus 2. That is what our polynomial solution would look like here when we divide. Let's go ahead and do the next example here. So then, since this says x minus 1/3, we're actually going to use a positive 1/3 as the number in our corner here. Pull your coefficients. So we have 3 for x cubed, 8 for x squared, 1 for x to the first, and we do not have, and we have 1 for our constant here. All right, drop down to 3 and let's multiply. 1/3 of 3 is a 1. When we add that together, we get a 9. 1/3 of 9 is 3. When we add that together, we get a 4. 1/3 of 4, or just do 4 times 1/3, that is just 4/3. And when we add that together, again, you can throw that in your calculator. 1 plus 4/3 is a 7/3. So our quotient part here, 3x squared plus 9x plus 4 plus our remainder of a 7/3. That would technically go over our divisor of x minus a 1/3. So the next thing we're going to talk about is the remainder theorem. So a nice thing about the remainder theorem is that when we do synthetic division, I'm going to use this example here to mention it here. So when we do synthetic division, as we did with this one here, we tested a -2, right? And when we tested a -2, what the remainder theorem says is it says that the number that you get as your remainder would be the same thing as if you were to evaluate with -2. Right, so like if I were to take this equation here and plug in -2 for x, right, and simplify all of that, my answer would be what you get is the remainder. So if I were to plug in -2, and you can go ahead and test that, you would get -24 as your answer for it. So that's what the remainder theorem is telling you. It is telling you that the remainder that you get when you test a number for synthetic division is the same thing that you would get if you were to evaluate that same number here. So let's go ahead and test that theory out here. So we are going to do a few of these examples here. I'm just going to do the first couple of them. If we're going to do, so we're going to use synthetic division in the remainder theorem to find each function value here. Now definitely if you wanted to, like it's asking us to find g of -2. So if we wanted to go ahead and just plug in a -2 here and simplify this, we would get the same answer. But we're going to use synthetic division. So that means we're going to do synthetic division with the -2. Drop down 2 for x cubed, -3 for x squared. It would be a 0 for x to the first, and then a 1. When we do synthetic division here, dropping down the 2, 2 times -2 is a -4. When we add this, I get a -7. -7 times -2 is a 14. When we add this, we get 14. When we multiply, we get -28. And when we add this column, we get a -27. That means g of -2 is a -27. And then go ahead and do g of -1, right? So if we do -1, again, same numbers here. 2, -3, 0, and a 1. Do synthetic division again. Drop down to 2. 2 times -1, we get a -2. We get a -5 when we add. +5 when we multiply. +5 when we add. We get a -5 when we multiply. And a -4 when we add there. We get a negative 4 as our remainder, so g of negative 1 is a negative 4. If you want to pause the video and try these bottom two on your own, test yourself here. I will give you the solution in just a second. If you would have done synthetic division here with g of negative 1/2, your remainder would have been a 0. Here with g of 7, we would be looking at 540 for that one. The factor theorem is our next important theorem here in this section here. What it tells us, it says that x minus a is a factor of the polynomial if, when you evaluate that number, when you do synthetic with division with that number, you get a 0 as its remainder. So let's go ahead and just jump into this. We're going to use the factor theorem to show that the first polynomial is a factor of the second polynomial. All right, so if we were to factor this thing here, we're saying that x plus 3 would be one of the factors, which means in turn, again, remember, if x plus 3 is a factor, right, and we were solving here, we would set that equal to 0 and solve, and x is actually a negative 3, which also tells us that negative 3 is a solution to this polynomial, which is one of the biggest reasons here why this theorem here is so important, because when we do find a number, when we do synthetic division and we find a number where we get 0 as the remainder, that's the magic number we're looking for. When we get 0 as a remainder, it means the number we just tested is a solution. Okay, so let's go ahead and do that here. So again, if we have an x plus 3, we're going to test negative 3. Our coefficients are a 1, a 3. Notice we're missing x cubed, so we're going to throw in a 0 for that. 1 for x squared, 8 for x to the first, and 15 for our constant there. All right, let's go ahead and divide. Drop down the 1 and multiply to get a negative 3. Add to get a 0. Multiply to get 0. We add, we get 0. When we multiply, we get a 0 again. When we add, we get 1. When we multiply, we get negative 3. When we add, we get 5. When we multiply, we get negative 15. And when we do add that last column, we get a 0. That is exactly what we're looking for. When we get a 0 as our remainder, that means negative 3 is a solution to our polynomial. So yes, x plus 3 is a factor of this polynomial. Jumping right into the next example, it says use the factor theorem to show that the first polynomial is not a factor of the second polynomial. So let's jump right into synthetic division. It gives us x plus 3, so we are testing negative 3. Again, our coefficients here, so let's see, negative 3, negative 9, positive 5, and a 12. When we do synthetic division here, dropping down our first number, when we multiply, we get 9. When we add, we get 0. When we multiply, we get 0. When we add, we get 5. When we multiply, we get negative 15. And when we add that, we get a negative 3. So our rightmost column is our remainder column here. We get negative 3. That's obviously not a 0. 0 is the only magic number we're looking for in this situation. So by getting something that is not a 0 here, it proves that this is not a factor of that polynomial. Now, it does tell us if we were to plug in a negative 3 into this polynomial here, we would get a negative 3, but it is not a factor. Our next example here tells us to find the value of k for which the first polynomial is a factor of the second polynomial. So in this sense, we have a polynomial that has some missing coefficients here, right? But we know that we want our factor to be x minus 2. Which means the number would be testing here is a positive 2. What do these coefficients need to be? What does k need to be in order to make this true? So let's set up the problem as we normally do. We're testing 2. Our coefficients are a 2. Here we have a k for x squared. We have a negative k for x. And then we have a negative 2. And let's go ahead and do synthetic division here. Drop down the 2. 2 times 2 is 4. Add this column. When we add this column, k plus 4, well, is k plus 4. Multiply here, right? 2 times k plus 4, right? Multiply that out, get 2k plus 8. That is what we're adding in this column over here, 2k plus 8. Add this column. Negative k plus 2k is 8k, and then we have our plus 8 there. Multiply. 2 times k is 2k. 2 times the 8 gives us 16. When we add this column here, drop down to 2k. Negative 2 plus 16 is a 14. Your rightmost column, again, is your remainder. So what we want to do is we want to take that remainder, 2k plus 14, set it equal to 0, and solve for k. Subtract that 14 on each side, and we get 2k is negative 14. Divide by 2 on each side, and k is equal to a negative 7. So that's exactly what k needs to be in order for this to be true. For our next example, we are going to talk about the rational zeros test. The rational zeros test tells us, essentially, I call this the P over Q process. P represents your constant number in your function. That's going to be in your numerator. Q is going to represent your leading coefficient here. So this is going to be a 2 in this instance. And what you want to do with those two numbers, always think last over first, right? P over Q, last over first, right? P over Q is just last over first. Last number over first number. Find all factors of that number. So what I mean by that, what all multiplies to get a 1? The only thing that multiplies to get a 1 is a 1 times a 1. So we don't repeat numbers, just write the 1. Look at your denominator. What multiplies to get a 2? The only thing that multiplies to get a 2 is a 1 times a 2. So our solution here, the set of all possible rational zeros here, which represents, right, if I were taking a look at this polynomial function and trying to solve this here, right, most of the functions we're about to look at here, they're not easily solvable, or, they're not typically solvable by factoring or able to throw into a quadratic formula or something like that. We're typically talking about higher ordered polynomial equations. So it's a little bit easier for us to do this rational zeros test, get a look at our possible rational solutions. So that's what this process here gives us. Our solution that we're about to get here tells us the possibilities of all the rational numbers that could be solutions to this problem. So after this point, what you want to do is take every number in the numerator, put it over the same denominator. So 1 over 1 is a 1. 1 over 2 is a 1/2. Throw a plus or minus number in front of it. That is your list. Positive and a negative 1, positive 1/2, negative 1/2. So we have 4 options here. Moving on to the next example. Let's do this again. Right, we're going to do the P over Q process all over again. Again, P is your last number, the 6. Q is your leading number, the 1. Everything that multiplies to get a 6, 1 times 6, 2 times 3. Everything that multiplies to get a 1 is just a 1. Now, when your denominator is just a 1, your list is the plus or minus of everything in the numerator, right? Because 1 over 1 is just 1, 2 over 1, 3 over 1, 6 over 1. So just essentially move over your numerator list, put plus or minuses in front of it. That is your full list of possible rational zeros. For g of x, our P over Q here would be a 2 over a 1. The only way to get a 2, again, is a 1 times a 2 over the 1 here. So that means our options are 1 over 1 or 2 over 1. So a plus or minus 1, plus or minus 2. Or this last example, again, P, last number is our 3. Q, first number is a 1. The only way you get a 3 is a 1 times a 3. Again, 1 times 1 is the only option there. So everything in the numerator over the denominator, 1 over 1, 3 over 3. Put a plus or minus in front, and there are your 4 possible rational zeros. So for this example, your P over Q, you would take 8 over 1. So again, factors of 8, 1 times 8, 2 times 4 would be your possibilities. Do synthetic division, testing those. Since we're dealing with a 4th degree function, you want to find 2 numbers using synthetic division to drop that down to an x squared. The two numbers that end up working out are a -2 and a -4. So keep in mind, those in factored form would look like x plus 2 and then x minus 4. But the actual roots are -2 and a 4. When we do synthetic division with these two, it leaves us with the quadratic equation, x squared minus 4x plus 1. So that does not factor. We would throw that into the quadratic formula to get our third and our fourth roots right over here. So our actual polynomial function in factored form would look like the x plus 2, the x minus 4. Then it's going to be x minus the 2 plus square root of 3, and then x minus the 2 minus square root of 3. And that's what your factored polynomial equation would look like. I'm going to leave this as an extra example. I'm not going to work this out here on video. But if you would like to know the solution of this, just to test yourself, the height would be x squared minus x plus 1, if you want to test yourself out with that example.